Hello, I'm Elias. I'm going to show you our work on extracting orchard tree skeletons from three-dimensional point clouds by using a state-of-the-art diffusion model. So let's start by looking at how an orchard typically looks like. It is composed by rows of trees that ideally at the end of the season look like this and are full of fruits to harvest. To make sure that there are actually many apples to harvest, a lot of management choices have to be made over the course of the season. Many of those management choices are made based on growth monitoring, which is still done mostly by experts. This, however, involves a lot of work, therefore automating this task would be beneficial to both farmers and also for the plant scientists working on developing new trees. To automate growth monitoring, we first need to collect data. This can be done by using drones or ground robots, and the data can be in the form of images or three-dimensional data like point clouds. For our approach, we use these point clouds, like the one you see here. And however, assessing the growth of the tree on these point clouds is hard still, as the branches are mostly occluded by the leaves, and therefore we want to infer a simpler representation from these point clouds. This is what is commonly called a tree skeleton, which represents the woody parts of the tree. The tree skeleton is a graph, as the one here, where the nodes are the orange dots and the edges are the black lines. When we have data like the example here, it is easy actually to reconstruct the skeleton, as the branches are all visible and all the points in the point cloud are part of the branches. So it is not surprising that this is the result. However, when there are leaves on the tree, this becomes way more challenging. Most of the branches are occluded, and even for us it is not really trivial to draw the skeleton in there. To tackle this problem, we use a generative model which integrates prior information about how apple tree skeletons look like. We specifically use a denoising diffusion model, which is a kind of model that is showing a promising performance in many applications, and it was originally developed in the image domain. And it works like the following. It learns a distribution of the training data first, and then to generate a new image, it starts with random noise, like the one here. Then it takes in so-called conditioning information, as for example might be an astronaut riding a horse, and then iteratively predicts denoising steps to go from random noise to the output image. So let's have a look at how we adapted this to infer actual tree skeletons. To reconstruct the skeleton of this tree, we start with the point cloud of the tree, here in blue. Then we sample random nodes from the point cloud as initial guess. You see them here in red. And then we sample what we call the flow directions. These are offset vectors that after convergence point from each node to the parent node. However, here you still see the initial guess, therefore they are still pointing all in random directions. And we then perform the diffusion denoising, which after convergence leads to a state where the red nodes are laying on the medial axis of the branches and the flow vectors are pointing towards the parent nodes. We then find the minimum spanning tree based on the nodes and flow directions to find a tree skeleton that you saw also before. So now that you know how the approach works, let's have a look at the real example. Here you see the nodes flying around in blue, and if you look closely you can see in red the flow directions. And now that the nodes are starting to approach the branches, especially in the top part, you can see that the flow directions actually align with the direction of the branches and end up pointing to the parent nodes, or in the direction at least of the parent nodes. Then, after the diffusion process converged, we extract the minimum spanning tree to find the final tree skeleton. You can see that the graph lies nicely on the branches. We compared our approach to other existing methods to perform tree skeletonization. On the left, you see the input point cloud for two different trees. Then next to them, you see our prediction in red and overlaid with the reference skeleton in green. And then towards the right, you see the prediction of smart tree, then the prediction of ant tree. You can see that ant tree actually performs quite bad because it fits branches into all leaves as well. Smart tree is less affected by this problem, but still introduces many wrong branches in the result. So the result of our approach is more accurate, and we also verified this in a quantitative evaluation. As metric to compare the approaches, we used chamfer distance, which measures how far the predicted skeletons are from the reference skeletons. The results confirm that our method is more accurate, actually, because you can see our chamfer distance in red, smart tree in blue, and edge tree in green. And yeah, for your information, the results shown here are in centimeters. So to conclude, we collected point cloud data in an orchard. We propose our developed tree skeletonization approach based on denoising diffusion, and we thoroughly evaluated our approach by comparing it against existing methods. So with this, I hope you found this interesting, and I'm happy to answer any questions you might have.